Well, hello, it's Cliff here, a toolmaker from New Zealand. In this video I'm going to go into making this edge clamp set or two-part vise. This one here, this was a previous one in a previous video. There'll be some machining tips and tricks, and you might be considering building your own. So follow me through the different stages of machining up these parts. Let's dial that in and test it. Yeah, so it's stayed square. It's really accurate, just like a conventional vise. What about pulling down onto the parallels? Well, I'm pretty sure that's going to be fine as well. Let's just stick that on 0. That's great. Oh, I wish I'd made one of these years ago. I would have used it all the time. In fact, in many ways, it replaces a vise. There are a few situations where a conventional vise would be superior, but this is far more versatile. It can hold such long parts. It holds the parts right down on the table if you want, so you've got more height under the spindle. It's just so versatile, and it pulls the parts down with both jaws onto the table or parallels. It's got all of those advantages over a vise, and it's accurate and holds really well. So I think it's fantastic. So I'm imagining some of you folk are going to want to build one of these. At the end of the video, I'll go through the technical drawing, the plans, which will help you build your own multivise. You can go to my website, download the plans via a PDF. So this is a nice easy part to quickly rough out. So you machine up 2 blocks of steel, machine them up with a fly cutter or a face mill into 2 square rectangular bricks, and then mark out with a felt pen the 45-degree angles. Then you can just bandsaw it, use a V block to saw the bevels until you end up with the 2 key parts, this part and this part, and then you have it all roughed out. You know, it literally a really short, simple job. If you don't have power feed on your bandsaw, it's well worth making one. It's the cheapest machine to automate so that you can go away and do something else while it's running. This is a really easy way to hold the main bodies because it balances the chuck jaws, and you can set the angle based off the ends there with a 45-degree gauge. Just makes everything accessible, and you can machine 2 at once. I'll be able to also cut the rebate there in the top. So that's the 6mm deep rebates cut in. So it's really straightforward because you can use your XY0 in the middle of the parts and then use the digital readout to get all the dimensions symmetrical, and there's virtually no measuring involved. So a nice quick easy job to get that all machined up. Oh, this is good fun. But it looks like it's going to have to be put to one side. We've got another lot of tool making works just come in. No fun allowed. Oh well, back on the back burner. So here I've just put in the holes for the T bolts at about 36mm centers. I've slotted them out a little bit just to make it a little bit more adaptable, and I'm using 7/16 Whitworth bolts, so that's about 11.8 clearance width slots or diameter holes. So if you're going to cut these slots, because it's so deep, it's best to use the quill and vertical feed the quill, taking about 1mm cuts as you slot it out so that it doesn't overload the side of the cutter and cause you a chatter meltdown. So that's how I set up the moving jaws, very similar, and again I could just machine them all to the digital readout settings, very little measurement involved. Set it up at the 45 degrees based off a parallel there, and so the rebates, or tongue and groove if you want to call them that, are slightly wider to allow, the tongue is slightly wider to allow for grinding after heat treatment, and the groove is slightly narrower, just by a few thou, about 0.1 of a millimeter per surface, for surface grinding after heat treatment. But if you were going to make these and you don't have a surface grinder or heat treatment, they would be almost as good made out of high tensile steel or P20 steel. M10 seems to be a fairly common thread for the cap screw to pull that sloping wedge block down. So just put in an end mill first to produce a flat, then drilled through the 8.5 tapping drill, and finally putting in this really short series guided tap wrench. Have a look at my recent video on the world's shortest guided tap wrench that just goes inside a drill chuck without winding your knee up and down very much. A very useful little tool. So there we are, a very short series guided tap wrench. Have a look out for my recent video. So here I'm deep slotting a 10mm slot, diameter slot, down 40mm deep. So I really have to use the quill on this one. I'll show you what I mean. I'll put the camera on the tripod and show you what I mean by sort of quill slotting. So I'm going to offset 1mm at a time. I'm going to go with a 6mm long slot. So this is the first millimeter. Second millimeter, and so on until I've traversed the 6mm, and then I'll just offset it 0.2 sideways in a series of, say, 3 cuts. So here I'm putting in some M6 threaded holes in the end clamping face of the jaws, so that I can later fit soft jaws or hard serrated jaws, or maybe shaped jaws, just to have the ability to do that. So again, I'm using this super short profile guided wrench. Just really quick and easy to put in. You don't have to raise the knee up and down all the time. And just for popping in a few threaded holes, it's a big time saver to have a tool like this. Have a look at my recent video on it, how you can make your own. Just a real time-saving tool. Guided tap wrench. Okay, now I'm going to carburize these parts by putting them into this little box that I've made up, which is partially filled up with some crushed hardwood lump charcoal and 5% approximately of sodium carbonate in the form of washing soda crystals that acts as a catalyst. That doesn't have to be completely full. I've found out from previous experiments that it very readily penetrates into the steel at about 880 degrees C, and I'll get in 1/2 mil deep within a couple of hours. I'll just screw the lid on. I don't even need to seal it. Have a look at my video, Case Hardening Mild Steel, while I go into all these different tests and experiments and find out what works really well. So it takes an hour or two to get up to temperature internally there, and then another couple of hours of soaking to get the carbon in quite deep. And then I just let it cool down overnight and do the same thing tomorrow. Just a good little background project. And the next day it's cooled down. The lid I don't seal the lid on, it seems to sort of weld itself on. I don't know how, whether it's something in a chemical process. So that's carburized now, I know from my tests, down quite a deep depth, goes down a lot more than 0.1 per hour. That'll be 1/2 mil to 1 mil deep carburized steel. And I'll do the other ones now. I better put new chips and catalyst in there just in case those chips are spent. So then we'll repack these parts and carburize these ones, and then I can heat them up and to a lower temperature and quench them in oil and harden them, and then the final stage is to temper them. I'm a little bit concerned about this. I've got my fire extinguisher ready because at the bottom of the oven the tile has broken into little pieces. I really need to get a replacement tile, and when I drag the big heavy parts out, I could send the red hot tiles firing in all directions, and that could be a fire hazard. So wish me luck. Oh God, that's heavy. Well, that one went okay. So 800 degrees, big block of steel into canola oil. We'll see if that goes hard. So hopefully that's gone nice and hard. Oh, that doesn't feel hard, that feels soft. How did that happen? Damn, first time I've had a failure. I'll test it a bit more carefully with a center punch. It might be hard. I don't think it's glass hard though. Yeah, checked it with the center punch. It's sort of hard on the very thin edges, but generally speaking not hardened. And that's really weird because I used exactly the same process as my tests. If you've seen my video, case hardening mild steel, where I do different trials, but this time it didn't work, and the only reason I can think of is that it's such a big block of steel that in the canola oil it just didn't get cool enough quick enough to freeze it in that hardened state. And so I'm going to try the next one into salty water, into brine, which is a much more severe quench, to see whether that makes a difference and hardens it. This may just have been too gentle a quench for the size of the block. Well, that was a lot more severe. So, yeah, whole 10 litres of water's got hot. And it's cooled down much more quickly. So let's see if that's made the difference. Yeah, that's hard. That's glass hard. So that's really interesting. Obviously, there's a certain size of block that's just too big for canola oil, and it won't cool it down quick enough. It holds enough heat to make too gentle a transition and not harden the steel. Well, I guess I've got to redo that first one again. Okay, well, should we go through the drawing? So you can see I've done an old-fashioned drawing here. I've got CAD software, BobCAD CAM, which is great for CAD and CAM, but it's not set up well for doing technical drawings and PDF output at all. So it's easier for me just to do an old-fashioned drawing board drawing. So I've refined and optimized some of the dimensions over this version 1. So we'll call this drawing version 2. Shall we call this the body and this the toe? And we'll call the product the Hallmark Multivise. And I've put a PDF, downloadable PDF, on my website, Hallmark Design. I'll put a link in the description below this video. If you go to the website, go to the resources page and click on the Hallmark Multivise page, and you can download the PDF. So you don't have to pause the screen and take a screenshot and print it off. You can get a better quality PDF from the website. Okay, so let's go through some of the materials here. So obviously you want to make it out of steel. I've made this out of mild steel and then case hardened it, and there's going to be another video going through making this product. So look out for that video. It should be out already. If not, it's not far away, going through machining it up and heat treating it. But you might not want to heat treat it. You might want to make it out of mild steel, and you could do that. You could machine the tongue and groove fit there with a very close fit is a really good idea, and put some anti-scuffing paste on it so that it doesn't wear there. You could also machine it out of high tensile steel or P20 steel even, and send it away to your local heat treatment company and get it nitrided. That would put a glass hard skin on it, or just make it out of high tensile steel, make it a close fit, and put anti-scuffing paste on those rebate slides. You want to make that tongue and groove a really close fit. As I explained in the video, any play there can relate to it moving or losing its position, losing its stiffness, losing its accuracy. So make sure you have a look at the build video, which will go through the machining tips and tricks as well. Okay, so let's go through some of the details here. So these holes, the centers are outlined here. Drill those holes to suit the studs of your milling machine. You know, that may be 10 mil or 12 mil or 3/8 or ½ inch or whatever. These are 7/16. You could slot them out to give you a little bit more versatility of positioning. And then this front cap screw here, position, that's a bit tricky, so have a wee think about this. So based off the position I've optimized, I've brought it back up the slope a little bit to give a bit more depth of thread there. And so the position of it from the end of this block, the base, to here is 20 millimeters. You want to machine a little flat to start with, and then drill and tap, say, an M10 thread for an M10 cap screw. 20 millimeters in from the end of the base, and the corresponding dimensions for this slot from this end, you're going to come into two different centers, one at 20 millimeters and one at 27 millimeters. That's them there. A little bit of clearance, say 10.4, and slot that out, and a bigger slot in the top to take your cap screw, clearance on your cap screw down, for example, 10 millimeters deep. So they're the key dimensions for the position of that cap screw for operating the toe. When you make these, you'll see on the build video that if you make a big brick the size of the toe and the base, you make it a bit longer. So the overall length of this assembly is 120 millimeters, but if you made it 130 or even a little longer, 132 millimeters long, then when you saw it off, there's enough material left in there to cut the tongue and groove rebate out, and it will return back to the final assembled length of 120 millimeters. So you need a block of steel at least 130 millimeters long by 60 wide by 43 high. Obviously you can change any of these dimensions if you need to suit your particular situation or material that you have on hand. So that's most of the details there. Because I have changed the dimensions slightly to try and further optimize the design for this version 2, I haven't prototyped it exactly. There may be a clash or an error issue, so please check everything as you go. Let me know if there are any issues. It should be okay, but you know, just be aware that this is an unprototyped, refined design. On the toe, I put some threads in here. Especially if you're going to harden it, I would put threads in there in advance of hardening it so that you can screw vise jaws on. You might want to do that in the future. You could have soft jaws screwed on the end of the toe, serrated hardened steel jaws, or a V jaws so that you can hold a round part. Or another option is, if you're making these, is to make it out of tool steel like O1 steel. Get a block of O1 steel and harden it. That's much easier to heat treat than case hardening mild steel. You just heat it up to the temperature and quench it and then temper it. But I think a lot of you are probably going to want to make it out of mild steel or high tensile steel. So make sure when you cut this rebate here that you use a very sharp cutter and get a very close fit. You could even lap or stone the last little bit so that you get a really close fit there. That's important. Another thing to consider is I've got the tongue in the toe and the rebate in the base. Now you could do it the other way around. I have deliberated over this a lot, and there's pros and cons either way. Think about that. You might want to change it. It might be better to have the tongue in the base. I'm not sure. There's pros and cons either way. If you're not sure, you're probably safer to stay with this current orientation, because at least we know this works. It gives you a little bit more depth under the head, which is a good thing, but it gives you a little bit less thread depth, which is a bad thing. There's pros and cons in everything in life, isn't there? So hopefully that's covered it basically for you there. So have a look on my website, Hallmark Design, for the PDF and print that off. So thanks for watching that video through to the end. You probably noticed I didn't include the surface grinding because most folk don't have a surface grinder, so you could finish machine it on the milling machine. But if you're interested in surface grinding, or you do have a surface grinder, or you just like to learn a bit more about surface grinding, I'll have a separate video on grinding up these parts and also other parts on the surface grinder. I think I'll call it Surface Grinding 101. Stay tuned for that video. Cheers.